Alright, this is chapter 16. This is on polynomial rings. So by way of intro, just to say this, we've seen some polynomial rings already. What we want to do is just formalize them. And look at some properties of them. Right, so some examples that we've looked at things like R of x. These are the polynomials that you know from pre-calculus. This is polynomials with real coefficients, or zx. It's polynomials with integer coefficients. So what we're going to do is define a sort of a more general statement, a more general structure, if you like. So I'll call this first set basic construction. So what I'm going to do this in two steps. I'm going to define the set itself, or a set if you like, make some comments about it, and then give a theorem / definition to go with it. So we're going to start with a commutative ring. You don't have to, but it makes things a lot prettier, so we do in this class. So we'll define Rx. So this right here, this notation, is typically read as R adjoined x. This is not the real numbers R, this is just a generic commutative ring R. So this is the set of polynomials whose coefficients are in R, the generic ring R. So having this familiar polynomial structure means we can add, subtract, and multiply using rules that we know from regular pre-calculus polynomials, right? So treating these as polynomials allows us to add, subtract, and multiply using standard polynomial rules. Except keeping in mind that the coefficients are in R. And that can be relevant, right? So the theorem that goes with this, I'm going to say definition / theorem, is that if R is a ring, so is R adjoined x, using these two operations. The proof of this I'm not going to do. It's just grunt work, showing that everything works. But I will do a simple example, just so we can see. And I'll do something that's not Rx or Zx. So in Z3 adjoined x, for example, we would do, if we wanted to say, for example, multiply 2x squared plus x plus 1 times x plus 2, we would distribute it. Just like we do with regular polynomials. But when I distribute in this case, I have to make sure that my coefficients stay in Z3. And you can do this either as you go, or like this one's no big deal. But when I multiply here, I get 4x squared for this first term. And 4x squared is the same as x squared because my coefficient is in Z3. And then when I add these, I get 2x cubed, I get 2x squared, I get 3x, but that's 0 x's, and then I get 2. And again, coefficients in Z3 is the kicker here. That's the thing to pay attention to. That's just a single simple example, right? So what we want to do next is just look at some properties of this. So 3 properties. And some of these, all except the first, will be sort of familiar from pre-calc, so we'll make some commentary on things that'll help jog your memories so that you can see that these are generalizations of things that you're familiar with, basically. So the first of these, very straightforward but not familiar, basically says if we start with an integral domain, then the polynomial ring that we construct is also an integral domain. Right. So to be really, really formal here, an integral domain is a commutative ring with unity and no zero divisors. Right, so I'm going to sort of fluff over some of the gory details, not the gory details, but the simple details, if you like. So the unity for dx is d's unity. So for example, in Rx, it's just 1 from the real numbers. Commutativity in dx follows from d. Basically follows from d and the operation. We could do this more formally. You could write down 2 arbitrary polynomials and you could multiply them each way and distribute and so on, but that's just a lot of grunt work, so not so pleasant. The really interesting thing is just making sure that we have no zero divisors. Right, so to show that d of x has no zero divisors, I'm going to multiply 2, get 0, and show that one of them must be 0. So assume that f of x and g of x are in dx. Let me start back here so I have space, with the product being 0. Now, but let's actually do this by contradiction. Let's assume that neither of them are. Now, these two guys are polynomials in d of x, right? So we can write them, they're non-zero polynomials specifically. So we can write these f of x, for example, as Rn x to the n plus ... down to x sub 0. Now Rn might be just a constant term. I have no idea what the degree of this is. And g of x could be a different degree. So we'll write Sm x to the m plus x. Sorry, I wrote x0 over here. This should be an R0. This should be an S0. These are coefficients. Now, when we do this, when we write f and g this way, when we multiply them, this is a giant mess, but I know from rules of multiplication that the leading coefficient will be the product of the leading coefficients. And the power will be x to the n plus m. And then I'll have a whole bunch of other stuff. Now, if this is 0, because we're assuming that this product is 0, that coefficient must be 0. So one of those must be 0. This is since D is an integral domain. But that's a contradiction. So it's a contradiction because the polynomials we're starting with, f and g, these are non-zero polynomials, which means their leading coefficients are not 0. So we've got a contradiction here. Now it's worth noting that built into this proof as well is the idea that when you're in an integral domain, that when you multiply polynomials, the degrees add. This doesn't happen if you're not in an integral domain. So let me sort of write that down real quick. So we'll note here, in d of x, when we multiply, this is for an integral domain, degrees add. in general, just to be clear, in Rx, this is an arbitrary R, this may not happen. Or this may not work, or may not be true if you like. So for example, say, if you're in, say, Z6X, if you take, say, something like 3x plus 2, the one I did in the notes, looks like this. 3x plus 2 times 4x plus 5, degree 1 times degree 1. I get 12x squared plus 8x plus 15x. So 15 plus 8 is 23, which is the same as 5. Actually, let me just write 23 for now, because I haven't reduced anything. Plus 10, and when we reduce this mod 6, right, we get x. Sorry, I did a bad math in there. That should be a 23. So when we reduce these coefficients mod 6, we get 0x squared, we get 5x, and we get 4. So the degrees did not add. Right, so in a generic polynomial ring, that may not happen. So second property is the division algorithm. So some of you may know this from number theory. So this is just nothing more than like an extension of this to polynomials. And it may be something that you're sort of familiar with method-wise from long division of polynomials, even if you're not familiar with it as a theorem. And so this specifically happens when you start with a field. So in other words, let f be a field, and let f of x and g of x be in f adjoined x. Now, for what it's worth, this guy right here, this is not a field. I only mention that because A said if you start with an integral domain, you get an integral domain. You might be tempted to think that if you start with a field that you get a field, but you absolutely don't, right? You don't have, polynomials like x plus 3 are not units. They don't have inverses, things like this. So I make no claims about f of x being a field. But if f and g are in f of x with g of x non-zero, I'm going to divide by g. So I can't divide by 0. This is the case here. So then there exists unique quotient and remainder with f of x is the quotient, that's a terrible looking cube, is the quotient times g of x plus the remainder. And so the property of the remainder, typically in the division algorithm, it's less than the divisor, it's less than the g if you like. But in this case it doesn't make sense, so the equivalent statement is that the degree of the remainder is less than the degree of the thing you're dividing. So the proof of this I'm going to omit. It's a bit lengthy. It's a bit awkward if you like. And there's nothing to be gained by doing it. But I definitely do want to do some examples. Right? Partly because it'll help you see why we need to have a field. And so what I'll do is I'll do an example, and I'll do it actually in two different rings, just so we can see, or different fields, starting with different fields, so we can sort of see how they compare. And the first one should be something familiar. So let me clear some space. So let's look at an example. So the first one I'm going to look at is in Rx. We're going to divide, say, x to the fourth plus 2x cubed plus 2x plus 1 by 2x squared plus 1. So this should be fairly familiar. This is just long division. I'm going to put a placeholder in here. You may know this as synthetic division. It's sometimes called, although it's sometimes written slightly differently. And the way that this works is, of course, we say first thing, what do I multiply 2x squared by to get x to the fourth? And that's 1/2 x squared We then multiply that by everything on the left. We get x to the fourth plus 1/2 x squared. Now, as we go, keep in mind that what's allowing me to make these coefficient choices is that I'm in a field. In other words, there is something I can multiply by 2 to give me 1 when I do these coefficients. So now when I subtract, then we say, what do we multiply 2x squared by to get 2x cubed? And that would just be x. So we have x times 2x squared is 2x cubed plus x. Subtract. And then we say, what do we multiply by 2x squared to give negative 1x squared? That would be negative 1/4. Multiply that. And then subtract. And now then we stop, right? There's nothing else we could do. We can't go into, having things divided by x, so there's no way we can proceed. But we can make a conclusion here that x to the fourth plus 2x cubed plus 2x plus 1, that is equal to our quotient, which we just created up top. Times the divisor plus the remainder. And so what we have here is our Q and our R. So that should be fairly familiar. So now what I'm going to do is I'm going to do the exact same calculation, but now I'm going to do it starting in a different field. So we'll do this. We'll do example in Z3x. We'll divide, same thing, x to the fourth plus 2x cubed plus 2x plus 1 by 2x squared plus 1. So I'm going to start with the same structure. I'm going to proceed the same way, except we need to be a bit more careful because everything is done in Z3. So I say, what do I multiply by 2x squared to give x to the fourth? So I definitely need an x squared, and then I need a 2, because 2 times 2 is 1, because I'm in Z3. So when I multiply this, I get 4x to the fourth, which is x to the fourth, plus 2x squared. Subtract. Now I do 0 minus 2 is negative 2, but that's the same as 1 because it's Z3. Then I say, what do I multiply 2x squared by to give 2x cubed? And that would just be x. Multiply that by, multiply that through, subtract. And we say, what do we multiply 2x squared by to get x? So this would just be 2. Because 2 times 2x squared is 4x squared, but that's just x squared. Plus 2. Subtract. 1 minus 2 is negative 1, but that's 2. So then we can write x to the fourth plus 2x cubed plus 2x plus 1 equals quotient. Times 2x squared plus 1 plus the remainder. Again, we've got the quotient and the remainder here and here. And the big difference, of course, between these two is that this one over here was done in Rx. And this one over here was done in Z3x. But the key point here is that having a field allows us to choose the coefficients. So it's this guy, or let's say maybe a better way is guarantees that the coefficient exists that we need. So it's only when you have a field that this is guaranteed. It may work in other cases, but there's no guarantee at all. So the next few theorems that are going to come up, they're really corollaries from this theorem. So what I'm going to do is I'm going to blank the screen out. I'm going to rewrite the division algorithm, and then we'll just go through these last couple of theorems. So this is just the division algorithm rewritten. So first of these, corollary. This is sometimes called the remainder theorem. And most of these should be somewhat familiar from pre-calculus. So let F be a field. All of these basically are going to require a field because they're all relying on the division algorithm. So let A be in F, and f of x be in f adjoined x. That's a polynomial. Then A is a 0 / root, whichever word you want, of f of x. Sorry, I'm ahead of my theorems. Let me back this up. Right hypothesis, wrong conclusion. I don't want to get these out of order. Then f of a is the remainder when f of x is divided by x minus a. So notice when you divide by x minus a, you get a remainder that has a lower degree, which means it must be degree 1, which means it must be a constant. And this is just saying that that remainder will be f of a. Right? So just for an example, before we prove this, just because this may ring a bell, is let's say we're in Rx. Right? If we divide, say f of x equals x cubed plus 2x squared plus x by x minus 4, the remainder will be f of 4. Right, it'll be 4 cubed plus 2 times 4 squared plus 4, guaranteed, whatever that value is. So the proof of this is actually really, really easy. Right? So by the division algorithm, we have f of x equals q of x times x minus a. So I'm dividing f by x minus a because that's what the theorem statement talks about. Plus a remainder, which will be a constant. Right? So this b right here, this is the remainder with degree 0. It has to be degree 0 because it's degree less than the degree of g of x. So if you plug in a, that first bond's 0, and then we're done. The remainder is f of a. Now, we won't use this directly so much, right? So this is sort of a bit, it's not difficult and it may ring a bell, but it's not intuitive in any, or really useful in any way of its own. But the thing that follows from it, this is the factor theorem. This will be useful. So same hypothesis, let f be a field, a be in f, and f of x be in the ring, f adjoin x. So then a is a 0 / root, whichever term you prefer, of f of x. In other words, i.e. f of a equals 0. If and only if x minus a is a factor of f of x. And this would be, in this case, a linear factor. I'm going to make a comment about that in a second. So the proof of this is pretty obvious, right? Because it's a root meaning f of a is 0, but f of a is the remainder. So we could say a is a 0 / root if and only if f of a equals 0. That's the definition, which is if and only if the remainder when f of x is divided by x minus a is 0, which is if and only if it's a factor. Sorry if the computer's picking up the noise there. That's QED. So I'll note here, before we go any further, is factors like this of the form x minus a are linear factors. Actually, factors of the form more specifically a times x plus b are linear factors. And since ax plus b, since I can rewrite this in a field, I can factor out the x. Basically, linear factors therefore correspond to roots. / zeros, if you prefer. So that's something to keep in mind when I give this final theorem, is that if you have a root, you have a linear factor. If you have a linear factor, x plus b, you have a root, negative a inverse b. So keep that in mind. So the final theorem, theorem E, which I'm going to call counting roots. So this should be pretty familiar from pre-calculus, basically in a standard way. So we'll say a polynomial of degree n in f of x, so with a field, has at most n roots, zeros. So a couple notes. And this should be familiar from pre-calc. Say in pre-calc, we know, let's say a polynomial like a cubic. This has at most 3 roots / x-intercepts. This is in Rx. So that should ring a bell. You know this about cubics. The second thing, before I give a proof of this, is if you don't have a field, this may not be true. So in a general ring X, this may be false. So for example, in Z6X, f of x equals x squared plus x has 4 roots / zeros. This is because if you plug them in, if you plug in 0, you get 0. If you plug in 2, you get 6, but that's 0. If you plug in 3, you get 12, but that's 0. And if you plug in 5, you get 30, but that's 0. So there are 4 of them there. So it doesn't always work if you're not in a if you're not starting with a field. So proof. So the proof of this, since we're counting roots and we know that roots correspond to linear factors, what we can just really do is count linear factors. So we're going to do this by induction on n, the degree. And we're going to do this with n greater than or equal to 1. For what it's worth, people always just sort of make a generic statement about a polynomial of degree n. When the degree is 0, you have sort of the sort of crazy case when the constant function is the function 0. And if it's the 0 function, you could argue that it has infinitely many zeros. And so to avoid this, let's just look at 1 and up. because that's all we really care about. So if n equals 1, then f of x, what would this look like, right? It would be linear, ax plus b. But we've already seen that this is just the linear factor itself. So one linear factor, hence 1 root slash 0. All right, so in the n equals 1 case, it's straightforward. Now let's assume it's true for k. In other words, a polynomial of degree k has at most k roots. And now let's let f of x be degree k plus 1. So one of two things is true. Either it has linear factors or it doesn't. All right, so if f of x has no linear factors, then it has no roots. Slash zeros, and we're done. Right, so suppose it doesn't have 0, right? So otherwise it has at least 1. So what we can do is we can put f of x, we can take that linear factor, we can factor it out. Right? We can write it like that. You can write it as x plus b if you like. Doesn't really make a difference. Right? Like this. So then, because the degrees are adding, right, so this is with the degree of q of x equals k. So then, because of that, by induction, by the induction hypothesis, q of x has at most k roots, zeros, slash linear factors, however you'd like to think about it. So therefore, f of x is x minus a times q. This has at most k plus 1. And that's the end. So that's sort of the end of this chapter. There's one last thing in the chapter about principal ideal domains that I'm actually going to put in the addendum, put in a part B, because it's sort of, I think it's maybe a bit odd that it's in this chapter, and so I feel like it should be separate, but it'll be fairly quick. So I'll put that in a part B, and this will be part A.